century. Theoretical physics has been defined by, well, by the greatest intellectual conflict in human history.
That's not an exaggeration either. We're talking about a Cold War between two titans.
Two intellectual frameworks that perfectly describe their own realms, but they absolutely refuse to work together.
On one side, you have general relativity, Einstein's grand, smooth, deterministic theory of the cosmos.
And on the other, quantum mechanics, the theory of the small, the chunky, the fuzzy, and the probabilistic subatomic world.
These two are the competitors, and for 100 years, the goal of basically every ambitious physicist has been to broker some kind of peace treaty.
Right, a unified theory of everything. We've spent years chronicling this skirmish, testing their boundaries at the moment of the Big Bang and the crushing gravity of black holes.
But based on the dossier of research we've put together, the war is, for all intents and purposes, over.
And the resolution is far more shocking than anyone really anticipated.
The verdict is, it's not a victory for either general relativity or quantum mechanics. It's the realization that the battlefield itself, space-time, may not be fundamental at all.
It might be a mirage.
Yeah.
An illusion.
Precisely.
So our mission today is a deep dive into the paradigm-shifting physics that forces this conclusion. We're talking about the holographic principle.
And its precise mathematical embodiment, the anti-de Sitter conformal field theory correspondence, or AD-SCFT for short.
We are tackling some truly existential questions here.
We are. We're moving past the standard textbook view and into physics that is genuinely mind-bending. It suggests our three-dimensional reality is just a sophisticated emergent projection.
A projection from a lower dimensional boundary.
Right. And understanding this changes how you view everything. What is gravity? What is information? And, fundamentally, what is reality if location and distance are just features of a user interface?
Okay, let's unpack this conflict first. I think without understanding the hostility, you can't appreciate just how radical the solution is. So on the macro scale, general relativity, Einstein, 1915.
And it describes gravity beautifully. It tells us that gravity isn't a force that pulls, but it's the geometrical manifestation of mass and energy.
It's the curvature of a smooth, four-dimensional structure we call spacetime.
And the key characteristics here are, one, it's a classical theory. It assumes continuity, meaning you can define properties like position and momentum with infinite precision.
And crucially, it's background independent. I love the stage play analogy for this.
It's a great one.
Imagine a play where the stage itself isn't fixed. It actually changes shape, it curves, depending on where the actors, the planets, the stars, the black holes are standing.
The geometry evolves dynamically with the matter inside it. The actors shape the stage as they move across it.
Okay, so then you try to smash that seamless, smooth theory into quantum field theory, the language of the standard model, and everything just goes haywire.
Completely. QFT is the realm of the small. It's inherently probabilistic, governed by the Heisenberg uncertainty principle, and it's fundamentally chunky.
Quantized.
The universe, according to QFT, is this sea of quantum fields, and particles are just localized excitations. They're the tiniest, most precise bundles of energy in those fields.
But this theory, it traditionally operates on a fixed, flat background stage, usually what's called Minkowski space.
And that fixed stage is its first major point of friction with GR. But the real mathematical crisis, the real breakdown, hits when you try to quantize gravity.
You mean when you try to introduce the particle that mediates gravity, the hypothetical graviton, and make it play by the quantum rules?
Yes, when you do that, the equations immediately rebel. They break.
This is the infamous non-renormalizability problem, right?
It is. In QFT, we calculate how particles interact by summing over every single possible path they could take. You've probably seen the pictures. These are the Feynman diagrams.
And when those calculations involve virtual particles, the answers often shoot up to infinity, which is, it's obviously nonsensical.
For forces like electromagnetism, these infinities are manageable. We have a technique called renormalization,
where you sort of redefine the basic numbers of the theory, like the electron's mass or charge, to absorb the infinite parts.
Exactly. And that works because in quantum electrodynamics, the interaction strength actually decreases at extremely short distances or high energies. The math converges, it behaves.
But gravity is fundamentally different. It's the on, one out.
Completely. As you zoom in, particularly toward the Planck scale, that incredibly tiny distance of 1.6 times 10 to the minus 35 meters, the strength of gravity increases without bound.
So the graviton, the particle we're trying to quantize, interacts with itself and every other particle so violently that the mass just explodes.
It generates an infinite number of different unmanageable infinities. You can't just brush them under the rug with renormalization. The theory breaks.
This failure signals a really deep fundamental misalignment. GR wants smoothness. QM demands discreteness.
And when you try to quantize GR, the math suggests that space-time at the Planck scale should become this violent, fluctuating quantum foam. But the equations offer no sensible description of that foam. They just collapse.
So that failure, that collapse, forced physicists to start looking for a radically different foundational structure.
It had to. The old way wasn't working.
And that theoretical Cold War, it turned into a genuine crisis when they started applying these incompatible rules to the most extreme objects in the universe.
Black holes.
Exactly. These predicted features of GR are the perfect testing grounds for quantum gravity.
They are. And classically, black holes are incredibly simple. They're summarized by the no-hair theorem.
Meaning they're defined only by three external observable properties: mass, charge, and angular momentum.
That's it. Everything else about the matter that formed it, the identity, the complex arrangement of atoms, what we call the information, it just seems to be lost forever behind the event horizon.
But then, in 1974, Stephen Hawking did something incredible. He applied quantum field theory to the edge of the event horizon.
And he found that space-time curvature doesn't just silence quantum fluctuations, it actually causes them to break apart.
These are the virtual particle-antiparticle pairs that are constantly popping in and out of existence in the quantum vacuum.
Right. And the horizon disrupts this game. One particle of the pair, let's say the negative energy one, falls into the black hole, while its positive energy partner escapes.
To an outside observer, this escaping partner is thermal radiation, what we now call Hawking radiation.
And crucially, that escaping radiation carries away energy. This means the black hole isn't permanent. It shrinks. It evaporates over vast, vast timescales.
And this leads directly to the information paradox, which forced physicists to abandon one of their core principles. It was a genuine fork in the road.
A huge one. If the black hole eventually evaporates completely, where did the information about the original matter go?
So option one, the information is just destroyed.
If that's true, you violate unitarity. And unitarity is the bedrock quantum principle that says information must be conserved.
It's the idea that quantum processes are reversible, right? If you know the final state of a system, you should always be able to calculate its initial state.
Exactly. Think of it like a quantum computer program where the inputs can't be calculated from the outputs. If a black hole destroys information, it's a non-unitary process. It breaks quantum mechanics entirely.
Okay, so that's a pretty terrible option. What's the alternative?
The alternative is that the information is preserved. It must be encoded somehow in the Hawking radiation.
But Hawking's own calculations showed the radiation was purely thermal. It's random, like steam from a kettle. It carries no unique signature of what fell in.
Right. You couldn't tell if the black hole was formed from a stack of encyclopedias or a star. The information seemed to be gone.
So physicists were forced into this impossible choice: preserve the smooth, deterministic geometry of general relativity and violate quantum information conservation.
Or maintain the ironclad conservation of information required by quantum mechanics and sacrifice the fundamental premises of gravity.
The paradox demanded a radical solution, something so comprehensive that it had to change our understanding of reality itself.
And that solution was the holographic principle.
Okay, so the theoretical structure of our 3D reality cracked wide open when physicists started thinking about black holes and thermodynamics.
The very first crack came from Jacob Bekenstein. He was wrestling with the second law of thermodynamics.
The universal law of disorder. It states that entropy, a measure of disorder, must never decrease in a closed system.
And Bekenstein realized that if a black hole had zero entropy, the second law could be violated trivially.
How so?
Well, you could just take a high entropy object, say a hot cup of coffee, and throw it into the black hole. The coffee would vanish, its entropy would vanish from the observable universe, and you would have just decreased the total entropy of the cosmos.
Which is a huge violation. So Bekenstein proposed that black holes must have entropy.
They must, and this entropy has to increase when something falls in. But here is the really counterintuitive clue.
He argued that this black hole entropy was proportional not to the volume of the space inside,
but only to the area of its event horizon.
That's bizarre. Classically, entropy is always a volumetric property. If you double the volume of a box of gas, you double the disorder, you double the entropy.
Right, but black holes defied classical thermodynamics. They demanded that their information storage capacity scaled with their two-dimensional surface area, not their three-dimensional volume.
And this is where we find what you call the Rosetta Stone of quantum gravity.
We do. Hawking's own work on radiation actually confirmed Bekenstein's hypothesis, and it led to the Bekenstein-Hawking entropy formula.
Now, this formula is a bit of a mouthful, but its composition is what's so revolutionary. S equals K times C cubed times A, all over 4 times G times H bar.
Let's just look at those constants. You've got Kb, Boltzmann's constant from thermodynamics.
You've got C, the speed of light from relativity.
You've got G, Newton's constant from gravity.
And you have H bar, Planck's constant from quantum mechanics.
This single formula ties together all 4 major, previously incompatible pillars of physics. It's the first numerical link between geometry, gravity, and quantum microstates.
What about that 14 factor in the denominator? What does that mean physically?
That's a great question. The factor of 1/4 suggests something deep about the information density. The formula tells us the black hole's entropy, its maximum storage capacity, is set by the area of its surface at a density of roughly 1 bit of information per Planck area. Now, if every microscopic degree of freedom were independent and classical, you'd expect a factor of 12. The 14 suggests a high degree of correlation or some hidden symmetry among the microstates.
So they're not all just independent bits.
No, the information encoding is highly efficient and structured. It's not just random noise, it's a clue.
The implication of this Bekenstein bound is staggering. It sets an absolute limit. The maximum information that can be packed into any region of space is defined by the area of its boundary.
Think about that for a second.
I am. So if the amount of information you can store inside a room is only limited by the square footage of the walls and not the cubic footage of the air inside, that means the 3-dimensional interior must be highly reduced.
Exactly. The information must really be stored on the surface.
So Gerard Hooft and Leonard Susskind formalized this intuition. This became the holographic principle in the 90s.
Right. They argued that if you continuously try to pack more and more information or mass energy into a region, you eventually cross a threshold and you form a black hole.
And once that happens, the information capacity is strictly limited by the area of that new event horizon, which is the boundary.
The conclusion is just inescapable. If information storage is defined by area, then the true fundamental description of the universe must be 2-dimensional.
Or at least D-dimensional, with the 3D, or D plus 1-dimensional world we live in, being a hologram. An effective emergent projection of data stored on a boundary surface.
And this isn't just a philosophical idea. We can use statistical data to quantify this dimensional reduction.
Okay, let's hear the numbers.
If the universe operated volumetrically, meaning every tiny Planck volume held 1 bit of information, our observable universe would hold about 10 to the power of 185 bits.
An incomprehensibly complex number.
Truly. Now, what's the holographic limit?
Based on the area of the boundary of the observable universe.
It's only 10 to the 123 bits.
That means the universe is over 10 to the 60 orders of magnitude, less complex than a naive 3D calculation predicts.
It's staggering. 10 to the 60. That massive redundancy is the fingerprint of the hologram. It means those 10 to the 185 volume states are physically impossible.
Because if you tried to achieve them, you would just instantly collapse the region into a black hole.
The only physical states allowed are those that can be encoded on the surface. And this finally gives us a path to resolving the black hole information paradox.
Right. The information isn't destroyed. It's encoded on the 2D surface of the horizon, and it escapes via the thermal Hawking radiation.
Which solves the violation of unitarity. It saves quantum mechanics.
Okay, so the holographic principle was this fantastic speculation, a profound insight needed to solve the information paradox. But it was still just a concept.
It was. Until 1997, when a physicist named Juan Maldacena turned it into rigorous mathematics with the odd-s-CFT correspondence.
The gauge-gravity duality. He didn't just propose a possibility. He showed a precise mathematical identity, an exact equivalence between two theories that look utterly unrelated.
It's duality in its purest form. So let's define the two sides. On one side, you have the bulk. The gravity side, this is type IIB string theory operating on a very specific geometry.
5-dimensional anti-de Sitter space coupled with a 5-sphere. We just call it eddy S5 times S5.
Right. This is a full-blown quantum gravity theory. That's one side.
And on the other side, you have the boundary. This is the purely quantum mechanical side. It's a theory called N4 super Yang-Mills theory.
It's a specific type of conformal field theory, or CFT, and it lives on the 4-dimensional boundary of that ADS space.
And Maldacena showed that these two theories, one with gravity in higher dimensions, one with only quantum fields in lower dimensions, are mathematically identical.
Isomorphic. And the significance of this is hard to overstate. This was the first successful, non-perturbative definition of quantum gravity.
So instead of trying to calculate quantum gravity directly, which, as we said, breaks down into all those infinities,
you just calculate the equivalent problem in the well-defined, finite quantum field theory on the boundary, and you get a sensible answer for gravity.
But wait, that N4 super Yang-Mills theory sounds impossibly complex. Why did he choose that specific one?
That's a crucial point. We have to be clear that N4-SYM is a highly simplified Tori model. It doesn't describe the messy reality of our universe.
Which is based on something called QCD, quantum chromodynamics.
Right. He chose N4-SYM because it has an enormous degree of symmetry, the maximum possible supersymmetry, in fact.
And those symmetries just cancel out a massive amount of complexity,
making the dualities mathematically exact and tractable. It's the simplest possible setting where you can rigorously define quantum gravity.
What's the conceptual leap you have to make when you're actually using this duality?
The great conceptual leap, the secret sauce, involves the coupling constants. In the gravitational bulk, gravity's strength is described by its coupling constant, Gn.
And on the boundary CFT, the quantum interactions have their own coupling constant, Gyn.
The duality states that when the gravity side is strongly coupled, when curvature is high, gravity is dominant, like near a black hole, the quantum field theory on the boundary is weakly coupled.
And it's easy to calculate.
And vice versa. Strong gravity problems become weak field problems. This inversion is why it's so powerful. It lets us calculate things that were previously completely intractable.
So, because these two theories are mathematically equivalent, physicists had to develop a kind of holographic dictionary to translate concepts back and forth.
Yes, between the gravitational bulk and the quantum boundary. And this is where we really start to understand how our 3D reality emerges from 2D data.
The best way to visualize this is the soup can analogy.
I like this one. Imagine a can of soup that extends infinitely. The interior, the soup, is the bulk.
This is the D plus one-dimensional space where gravity exists, where things have volume, where black holes can form.
And the label on the can is the boundary. This is the D-dimensional surface where there is no gravity, only a highly interactive quantum field theory, the CFT.
And the correspondence is the statement that everything happening in the gravitational soup is perfectly and completely described by the patterns of quantum information on the label.
So if the label on the soup can is all the fundamental data, the 3D soup inside is really just the computational result, the emergent physics of that label.
Exactly. And the dictionary gives us the precise translations. For example, a black hole in the bulk isn't a hole on the boundary.
No, it translates into a purely thermal state on the boundary, a hot, high-entropy fluid.
And it works with that strong weak duality we just talked about.
It does. When the black hole is small and highly curved, that strong gravity in the bulk, the boundary is weakly interacting. When the black hole is huge and less curved, weak gravity, the boundary is strongly interacting.
But let's look at the basic building blocks. What about a fundamental particle in the bulk, like a graviton?
In the dictionary, that translates to a complex composite particle on the boundary, often called a glue ball.
And conserved quantities like mass or energy.
Those become conserved currents on the boundary. But the deepest insight in the dictionary, the one we'll spend the rest of our time on,
is that entanglement patterns in the quantum boundary correspond directly to connected geometry to spacetime in the gravitational bulk.
That's the one.
Now, a critical detail here is the requirement for anti-de Sitter space. We can't use flat spacetime or Minkowski space like we usually do for QFT. Why is 8S so necessary for this to work?
8S is a spacetime with constant negative curvature. The easiest way to think of it is like a saddle shape that repeats infinitely.
And that negative cosmological constant, lambda less than 0, is the key. It causes gravity to always pull things together.
Which is very different from our own universe. As we'll see, structurally, 8As acts like a perfect, stable container.
A mirror box.
A mirror box or a perfect gravitational well, exactly. Its spatial boundary is located at infinity, but because of the negative curvature, light can actually travel from the center, hit that boundary, and return in a finite amount of time.
Which creates a stable, closed, non-collapsing system. And that stability is essential for defining the field theory on the boundary.
It is. And the second reason is symmetry. The C in CFT stands for conformal field theory.
Right.
The specific geometry of ADA space exhibits conformal symmetry. It looks geometrically the same at all scales.
So the physics of large objects is structurally identical to the physics of small objects, just scaled up or down.
And that exactly matches the property of a conformal field theory, which is scale invariant. The physics is identical whether you look at it at the nanometer or the kilometer scale.
So it's this symmetry lock plus the stability of the box that made the Maldacena conjecture so mathematically sound.
That's right.
Okay, so we've established that the 3D world is a projection, and we have a rigorous mathematical model at a CFT to describe it. Now we have to uncover the mechanism.
The projector.
Right. If the soup is a projection of the label, what is the projector that turns quantum data into gravitational geometry?
The answer is quantum entanglement.
Einstein's spooky action at a distance.
And this realization represents a truly radical philosophical and physical shift. Traditionally, we viewed entanglement as a phenomenon that happens inside the container of spacetime.
But the holographic view flips this completely.
Spacetime is not the container, it is the manifestation of entanglement. Entanglement is the thread, and spacetime is the fabric woven from it.
So a distance in the bulk is just a visual proxy for the degree of correlation on the boundary.
That's it. And this connection moved from just a conjecture to a rigorous calculable tool in 2006, thanks to physicists Shinsei Ryu and Tadashi Takeyanagi.
The RT formula. SA equals the area of gamma A over 4GN. We heard a similar formula for black holes, but this time SA refers to entanglement.
Yes. SA is the entanglement entropy of a specific subregion, call it A, on the boundary. It measures how strongly that section of the quantum field is correlated with everything else. It's a purely quantum mechanical quantity.
And gamma?
Gamma is a surface in the bulk that is anchored to the edges of that region, A, on the boundary. It's the surface of minimum area that hangs down into the bulk, like a soap bubble suspended from a wire loop.
And the formula states that these two previously unrelated quantities, quantum information on one side, geometric area on the other, are exactly equal.
Yes. The insight is just profound. The geometry of space-time, how far that soap bubble dips into the bulk, is literally a measure of quantum correlation on the boundary.
So short-range entanglement on the boundary creates shallow dips into the bulk.
And deep, long-range entanglement creates dramatic curvature and probes the entire interior of the space.
This is phenomenal. It means space-time curvature is a physical measure of how quantum information is distributed and entangled on the boundary. Geometry becomes a proxy for the wiring diagram of quantum information.
That's a perfect way to put it.
And this realization that geometry is defined by entanglement was powerfully illustrated by Mark van Ramsdonck's thought experiment.
Right. If entanglement is the glue, what happens when we remove the glue?
What happened?
Van Ramsdonck's analysis, based directly on the RT formula, was striking. Imagine taking two separate entangled regions of the boundary and manually reducing the entanglement between them to zero. You cut the quantum connections.
The minimal surface connecting those two regions in the bulk would shrink.
It shrinks, it pinches off, the space-time literally tears itself apart and separates into two disconnected pieces.
So the conclusion is almost unavoidable. Entanglement is the glue that binds distinct points of space together, giving us the continuous connected space-time we experience.
And gravity isn't just a force, it's the resistance to the tearing of that quantum glue.
This all culminated in that 2013 conjecture by Maldacena and Susskind. ER equal EPR.
Exactly. It states that Einstein-Rosen bridges ER, or wormholes, which are geometrical connections in GR, are equivalent to Einstein-Podolsky-Rosen pairs EPR, or entangled particles, which are quantum connections.
The logic flows directly from the RT formula. If geometry is entanglement, then a geometric connection, a wormhole, must be the same thing as an entanglement connection.
Precisely. Those famously entangled particles aren't communicating faster than light through our space. They are connected directly through a shortcut, a micro-hole, that their entanglement is in the higher dimensional geometry.
So our 3D geometry is the emergent physical manifestation of the underlying quantum wiring diagram.
That's the essence of it.
Okay, the ATA-CFT correspondence and the RT formula are mathematically beautiful, but they operate in the realm of continuous mathematics. To really understand how the hologram works pixel by pixel, on a discrete level, physicists had to turn to a different tool.
They did. They turned to computational tools called tensor networks, which they borrowed from condensed matter physics.
And a tensor network is essentially a mathematical tool used to model complex quantum systems efficiently.
Right. It represents a quantum wave function, the state of the entire system, as a graph. The nodes in this graph are tensors, which are just multidimensional arrays holding small chunks of data.
And the lines connecting the nodes.
The lines represent entanglement indices. So the geometry of the network graph explicitly encodes the entanglement structure of the quantum state.
And this is key because it lets us visualize how microscopic quantum information on the boundary can build up the macroscopic geometrical space of the bulk.
We're moving from continuous calculus to discrete computation to understand reality.
Now, there's a specific, powerful type of tensor network that provided the most astonishing breakthrough here.
Mech-NERA, the multi-scale entanglement renormalization ansatz.
It was originally designed to simulate quantum systems that look the same at all scales.
Exactly, the scale invariant property of the conformal field theory on the boundary.
And then Brian Swingle made this crucial observation.
He saw that the graphical structure of a Mayer network is mathematically identical to the discretized geometry of spatial anti-de Sitter space. It wasn't an approximation or a close resemblance.
It was a perfect structural match for that soup can geometry we talked about.
It was.
Let's try to visualize this for everyone. A Mayer network is usually drawn as a layered pyramid. The bottom layer, the open legs, represents the boundary CFT.
This is the microscopic, high-energy, or ultraviolet UV scale of the physics, the finest grain.
And as you move up the layers of the network, you're performing a process called renormalization,
which is essentially coarse graining. You're taking microscopic data and smoothing it out to find the large-scale emergent behavior. Crucially, moving up those layers is literally moving deeper into the bulk geometry.
So the layers higher up in the network represent the macroscopic, low-energy, or infrared IR scale. And
the tensor connections themselves in the Mayer architecture, they perfectly model the geodesics, the shortest path distances that are required by the Ryutaka-Yanagi formula.
This suggests something profoundly non-trivial about that extra dimension in the hologram.
It does. It suggests that the radial dimension in ADS, the depth into the hologram, is not just another spatial direction like length or width. It is a dimension of scale.
So moving inward is just the computational process of zooming out and averaging the microscopic information stored on the boundary.
You're moving along the renormalization group flow.
This framework is highly satisfying because it shows how 3D space emerges from 2D data. But does it describe really complex gravity, like the inside of a black hole?
That's the next test. We established that black hole physics needs volume law entropy inside the horizon, not the area law that defines the horizon itself.
And standard Miro reproduces the area law of entropy beautifully.
It does. To model the full complexity of a black hole interior, which is filled with a vast volume of thermal gas and volumetric entropy, we need a slight adjustment: branching Mira.
How does the branching structure model the physics of a black hole?
As the network renormalizes and moves deeper into the bulk, it's allowed to split into two disconnected parent branches. This branching or decoupling structure is what's required to encode the huge number of internal microstates consistent with the volume law entropy of the thermal interior.
So it models the dramatic increase in the degrees of freedom inside the event horizon.
Exactly. The complexity of the network is geometrically mapping the physical complexity of the gravitational space. The Mira structure gives us the pixels and the computational flow that turns quantum mechanics into the gravitational container we experience.
The ADS FEFT correspondence is a triumph. It provides a non-perturbative definition of quantum gravity, it explains entanglement, it resolves the information paradox, but now we have to confront the biggest existential challenge to the whole framework.
We do not live in anti-de Sitter space.
That's the fatal flaw. Our universe, according to all observational data from the cosmic microwave background in supernovae, has a positive cosmological constant.
Lambda, greater than 0. It's expanding, and that expansion is accelerating, driven by what we call dark energy. This geometry is known as de Sitter space, or DS.
The differences are structural and profound. ADS is the box negative curvature, everything pulled together, stationary, stable.
And DS is the bubble positive curvature, accelerating expansion, everything being pushed apart.
And crucially, DS space has no stable spatial boundary like ADS does.
Right. If you fly infinitely far in ADS, you get that wall where the CFT lives. In DS space, space just keeps expanding forever.
So instead of a stable wall, our boundary is defined by a cosmological horizon,
which is the limit beyond which points in space accelerate away from us faster than light. They lose causal contact with us. This horizon is where information is lost to the accelerating expansion.
So if we are a hologram, but we don't have a stable spatial boundary like the label on the soup can, where is the holographic screen for our reality?
This led to the DS-CFT correspondence, which posits a truly radical answer.
Which is?
The holographic boundary of our accelerating universe is not located at spatial infinity, but at future infinity, what we call I+.
That introduces genuine existential vertigo. If we are a hologram, the quantum screen containing the data of our entire reality is located at the end of time.
We are a holographic projection from the infinite future.
It forces us to ask deep questions about causality. If the universe's fate, its ultimate conformal boundary, is encoding its present and past state, does that mean the future boundary already exists in some abstract sense?
And we are simply living out the projection determined by that ultimate state. It's like the end of the movie determines the sequence of frames.
The DSCFT correspondence is philosophically incredible, but it's not as mathematically robust as AD-SCFT yet, right? It faces some major technical hurdles.
It does, especially when you try to incorporate string theory. The first hurdle is often called the swampland.
String theory is our best candidate for a full quantum gravity theory.
But when theorists try to construct consistent, stable, eternal de Sitter universes within string theory, they find it incredibly difficult. Many leading theorists now believe that DS space belongs to the swampland.
The set of theories that look consistent on the surface, but can't be completed into a full, rigorous theory of quantum gravity.
Which suggests that if the holographic principle holds, our DS universe might be inherently unstable, temporary, a metastable vacuum, perhaps.
Which aligns with some cosmological models.
Exactly. It might not be a permanent feature, but a temporary state decaying toward flat space, or even back to anti-de Sitter space.
And the second hurdle is highly technical, involving that RT formula applied to de Sitter space.
Yes. When physicists use the Ryu-Takayanagi formula to calculate the entropy of the cosmological horizon in DS space, the entropy often comes out as a complex number.
Specifically, S equals A over 4G plus I times pi over 2, where I is the square root of -1.
And entropy absolutely must be a real positive number. It's counting the actual microstates, the possibilities of the system.
For those of us who aren't mathematicians, why is that I, that imaginary component, so catastrophic?
Well, in standard unitary quantum mechanics, probabilities must always sum to exactly 1. If the entropy, which is derived from the number of microstates, is complex, it means the underlying probability calculations are breaking down.
Which strongly suggests that the dual quantum field theory describing our universe is fundamentally non-unitary.
It implies that probability conservation is violated, or that the system is evolving irreversibly. It's a massive blow to standard QM.
And it potentially aligns with that idea of a decaying, metastable vacuum.
It does. The complex entropy is a mathematical scream that our universe's quantum description might be inherently non-conserving in the long run.
The difficulties of DSCFT, combined with those fundamental paradoxes at the Planck scale we discussed, lead some of the world's leading physicists to argue that holography, while correct, is only a stepping stone.
They argue we must abandon spacetime entirely. This is physicist Nima Arkani Hamad's famous slogan, "Spacetime is doomed."
And his argument isn't based on philosophy, but on a rigid operational analysis of measurement, the breakdown of locality.
Right. To say spacetime is fundamental, you have to be able to measure points and distances within it.
And the physics breaks down when we try to measure distances at the Planck scale, that 1.6 times 10 to the minus 35 meters.
Yes. To measure a tiny distance with high precision, you need a probe particle with a very short wavelength. Shorter wavelength means higher energy.
So to measure at the Planck scale, you need Planck scale energy.
But general relativity intervenes. In the presence of gravity, energy equals mass. And if you concentrate Planck scale energy into a Planck scale volume,
you instantly create a black hole.
You do. And the black hole's event horizon is always larger than the region you were trying to measure.
And if you add more energy to try and get a finer detail, the black hole just gets bigger, obscuring the region even more.
It's a physical limit built into the laws of nature.
So, operationally, the concept of distance, or location, has no physical meaning below the Planck scale. Locality, the idea that interactions only happen at specific points, is an observable feature that disappears when you try to measure it precisely.
And if space-time cannot be precisely measured, it cannot be fundamental. It must be an emergent approximation, a feature of our smooth, low-energy world.
If space-time is an approximation, what structure replaces it?
The answer points to a geometric object that replaces both space-time and the cumbersome old-school machinery of quantum field theory, the Amplituhedron.
Traditionally, calculating particles scattering like two gluons colliding to produce three more was done using Feynman diagrams.
And that method requires you to assume both locality, that interactions occur at points, and unitarity, that probabilities are conserved.
And these calculations, especially for high-energy interactions, are nightmarishly complex.
For something like 5 to 5 gluon scattering, you generate hundreds of pages of algebraic terms. Each one represents a different possible path the particles could take. But here's the extraordinary detail.
When you get to the final answer, almost all those terms cancel out perfectly.
That massive mathematical redundancy strongly suggested to physicists that the concepts we assume are fundamental, locality, time, space, are actually generating unnecessary, cumbersome constraints on the math.
And the revelation came from Arkani Hamed and Jaroslav Trinka. They discovered that the final, simplified answer to these scattering problems could be found by calculating the volume of a single geometric object.
The Amplituhedron.
So instead of calculating complicated processes occurring over time and space, you just calculate the volume of a static, abstract shape, and you get the exact probability of the particle collision.
That's it. This jewel is a multifaceted polytope that exists not in four-dimensional space-time, but in a strange, abstract mathematical realm called the positive Grassmannian.
And crucially, its definition contains no reference to space coordinates or time coordinates.
The brilliance here is that when you define the Amplituhedron geometrically, the features that physicists struggled with for decades, locality and unitarity, you don't need to manually put them in.
They emerge from the geometric properties of the object itself.
It's a complete reversal of perspective. Physics is no longer about objects moving and interacting in space and time. It's about calculating the volume of a static, timeless, geometric object.
And space and time are emergent properties, like the smoothness of a film emerging from discrete frames.
The theoretical master amplituhedron, with infinite facets, is speculated to encode all possible physical processes and laws. In this view, the universe isn't a machine running forward in time.
It's a static, eternal mathematical structure.
And our perception of events, of things happening, is merely our limited, low-energy slice of this geometry. We mistake the computational flow required to interpret this timeless jewel for the flow of time itself.
Okay, we have to address the immediate philosophical leap. If our 3D reality is a projection from a lower dimensional boundary, are we living in a simulation? Like the Matrix?
This is a critical distinction that the physics defines quite clearly. The concept is duality, not simulation.
A simulation implies a hierarchy, a real world, the computer running the code, and a fake world, the characters inside the game.
But in ATA-CFT, the bulk, gravity, and space-time, and the boundary, the quantum field, are mathematically isomorphic. They are strictly equivalent descriptions of the same underlying reality.
One is not fundamentally more real than the other.
Exactly. We are not fake beings in a real computer. Now, the physics does favor the boundary as the more fundamental description because it's unitary, concise, and well-defined, while the bulk is emergent and fuzzy.
So think of it this way. The quantum field on the boundary is the sheet music, the fundamental structure.
And we, the 3D reality, are the symphony played by that music. Both are real, but one provides the defining structure for the other.
This entire deep dive began with dualism, the century-long struggle between gravity and quantum mechanics.
And the conclusion of this investigation into holography and the Amplituhedron is a profound move toward monism. It suggests the distinction between container and content, force and matter, is collapsing.
The foundational insights all confirm this unity. Geometry, general relativity, the container of gravity.
Is made entirely of entanglement, which are quantum correlations, the fabric.
And particles and their interactions, matter, the content of quantum field theory,
are defined by the static geometry of the Amplituhedron.
What really stands out to me is how that radial dimension in the hologram turned out to be the dimension of scale. We aren't separated from the quantum source.
We're just living at the smoothed-out, low-energy end of the renormalization flow. The ultimate conclusion is that the universe is a single, unified mathematical structure.
And the separation into distinct forces, distinct particles, and a distinct stage like space-time is just a result of our limited perspective as low-energy observers living inside the hologram.
We're observing the emergent properties of that deeper, timeless geometry.
As we close the file on this century-long investigation, the evidence is overwhelming that our common-sense reality is just a highly effective approximation.
Let's reinforce the three core insights we've extracted today. First, information is the fundamental quantity. That's proven by the Bekenstein bound, which shows area limits volume capacity.
Second, gravity is definitively emergent. The Rita-Kanagi formula shows that the curvature of spacetime is simply the hydrodynamics of entanglement entropy.
And finally, space-time is an illusion. Concepts like locality and distance break down at the Planck scale, and objects like the Amplituhedron prove that space and time are an emergent user interface for a deeper, timeless geometry.
And this brings us back to the ultimate provocation, the de Sitter dilemma. If the most mathematically rigorous framework for quantum gravity relies on a duality with a boundary located at future infinity, how fundamental is our experience of the arrow of time?
If our reality is a holographic projection originating from the boundary located at the end of time, then we are effectively the shadows cast by the infinite future. Does the past truly exist independently, or is the arrow of time itself just an emergent feature of a cosmic calculation running forward from the final totalizing state?
That is something truly mind-bending for you to mull on as you look around at your seemingly solid three-dimensional world.